Welcome to the podcast on the normal approximation of the binomial distribution. This is going to be a two-part podcast again, and this is part one of it, okay? So, first thing we need to do is go talk about what the mean and the standard deviation of a binomial random variable are. These two little formulas are going to turn out to be very handy and a real good idea to have them top of the head, okay? So the mean of a binomial distribution, or sometimes if you recall, we also call this the expected value, or you could say E of x, okay? That's equal to n times p, which is the number of Bernoulli trials times the probability of success. Makes a good intuitive sense if you think about it. Say, it's a real simple example. Say you go to a hospital and you take a simple random sample of 100 birth records. You would expect 50 of those birth records to be girls and 50 of those to be boys. Notice the expected word there. Now, why is that? Well, because here, notice your situation was n was equal to 100. One in there would be better. And your probability of success that I'm inferring here is that the population probability of success should be about 50% boys, 50% girls, right? So what is n times p here? It would be equal to 50, okay? So you've got a good intuitive sense already why that's got to be a true statement. Standard deviation for the binomial random variable, is going to be the square root of n times p times q, where q is equal to 1 minus p. Remember, p and q are complements to each other, okay? In other words, p is the probability of success and q is the probability of failure. All right, we're going to need both of those, so hang on to that. You might want to make sure those show up in your comp book. They're kind of important little formulas, and they're really easy to remember too, okay? All right, so let's start off looking at an example of a problem that we would use the binomial distribution for. Let's say we have a wart remover that states it works on 95% of warts. If a total of 10 subjects are selected, what is the probability that 9 of the subjects have their warts removed? I'm going to modify this slightly, 9 or more. So we're going to make it go out to the right. Okay, so a slight modification there, but because it'll make it a little more interesting if we do. Okay. So what's the probability of 9 or more of the subjects will have their warts removed? Well, let's check this out. This is a binomial distribution here. We've got n is equal to 10, and the probability of success is equal to 0.95. How do we know it's that particular distribution? What is it that keys us off to that? Well, we have a fixed number of trials. There are 10 subjects. Each of them are independent from each other, and they have a probability of success that remains fixed of 95%. Okay, so those are the three things that you need to know in order for it to be binomial. So how do we actually do the calculation? In other words, how do we find the probability that x will be greater than or equal to 9? Well, as I've been doing in the past presentations of this material, let's go ahead and do again, and let's write out the binomial model that corresponds to b of 10 by 0.95. Well, we know that it's a discrete distribution, and so if you want to write out its mass function or its probability distribution, you know that the x takes on what? Well, number of successes. So there could be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, or 10 successes, right? So the probability of x being greater than or equal to 9 is the probability of those two events right there, okay? And then notice that here in the green, that's everything else, isn't it, okay? So the probability that we're looking for, the probability that x is greater than or equal to 9, if we take that and we add that to the probability of x being less than or equal to 8, then we know the sum of those two probabilities has got to be equal to 1, which tells us that the probability of x being greater than or equal to 9 has got to be equal to 1 minus the probability of x being less than or equal to 8. Okay? So that's the calculation we're going to do, because if you recall from our previous work that we've done, that this green probability right here is exactly what binom CDF likes to work with. It insists that we sum from the left, and then we're starting from 0 up to whatever number you give it. So let's go ahead and get the calculator to do that for us. So I'll get the calculator up here for you. And we're going to have 1 subtract second distributions. And let's go to the binom CDF here. Okay. And let's see, we're going for what? There was an n of 10, a probability of success of 0.95, and we went up to 8, didn't we? Okay, because we wanted 9 or 10. Now, just as an aside, you could have probably easily done this one using Binomial PDF and calculate each of the individual probabilities for 9 and 10 and just add them together. But it's not a bad idea to review how this thing works, right? So hit and enter, and we get what? 91.4% of the time, you'll see 9 or 10 of the folks get their warts removed, okay? So the probability of x greater than or equal to 9, let me back in black here, was equal to, one more time to the calculator, so you see there, what do we have? We had 0.914, right, if we round off to 3 places. So we'll go 0.914, or if you were to say that to the general public, you would say 91.4% of the time you would expect to see 9 or more of the folks who are using this treatment have their warts actually removed. Okay? All right, now we're going to start talking about why are we talking about the normal approximation to the binomial here. Well, first of all, let's remind ourselves about the difference between a discrete random variable and a continuous random variable. And the random variable with the binomial is discrete. A continuous random variable, on the other hand, is not discrete, it's continuous. Which means instead of using this mass function like I did in the previous example here to represent my distribution, I'm going to use a curve. I'm going to use a probability density function or some sort of a curve such that the area under the curve is equal to the probability of the random variable taking on values in a particular interval. We know the values are continuous and the probabilities are between 0 and 1 again, so the total area under the distribution has to be 1. Now the uniform and the normal distribution we studied back in chapter 6 were both continuous. What we want to do is show that the normal distribution turns out to be a really good model of binomial distributions provided certain conditions are met. So to show that that's a true statement, we're going to get out the calculator here, okay? And I've written a little program on the calculator called Bino, very simple little program here. And what it wants to know from us is it wants to know what n is for your distribution, and it wants to know what p is. So, for example, if I put an n of 10 and a p of 0.5, then I've told the calculator that this is b of 10 by 0.5, okay? And what it's going to do for me now is it's going to go ahead and draw the probability histogram that corresponds to that distribution. Now looking at that probability histogram, we know this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And in many ways, this is the same as that mass function I gave you a minute ago, except for the probabilities are represented by the heights of the bars on the vertical axis, okay? Now one thing that we notice is that this looks pretty bell-shaped unimodal, doesn't it, right? As a matter of fact, it's looking dang near close to being normal, all right? Well, let's try this program again. Let's do it one more time. But let's take a look at the situation that we just had, where we had an n of 10 and a probability of success of 0.95. And let's see what that probability histogram looks like. And you go, ooh, no, not so, buddy. In this case, it's not looking very normal at all. As a matter of fact, we would say that's horribly skewed to the left. Let's take a look at another example. Let's say we had n equal to 10 and the probability of success equal to, say, 10%. What would the graph look like? And you go, yeah, no, wouldn't use a normal approximation there either because it's looking horribly skewed to the right. So the question comes is, when does it look like the distribution is well shaped by or well approximated by a normal distribution, and when is it not? Okay, so let's try a couple more and maybe we'll get an idea here, and then we'll give you the rule that Martha and Brenda are espousing, our authors, as to when you can use the normal approximation and when you can't. So let's go ahead and take a look at a distribution, say, with an n of 25 this time and a probability of success of, say, 0.2. Okay? We graph that and you're going, oh, look at that. Now that's still looking pretty bell-shaped. It's a little bit skewed, but that's not bad, isn't it? I could actually probably get away with using a normal distribution on this distribution here. I mean, this distribution being modeled by a normal distribution would probably not be a horrible idea. I could probably do that, okay? Let's take a look at another one. Let's do one more here, just to kind of see if we can figure it out. Let's go with an n of, say, 30 and a probability of success of, say, 0.2 again, okay? And then it's starting to look even more bell-shaped, isn't it, right? Let's do it one more time. I have to admit I'm Getting a little worried that my calculator is going to blow up here, but we'll go for it. We'll try 35. There's a certain point where it won't plot anymore, and I forget what that point is. We may be bumping up against it here. So we'll go n to 35 with a p of 0.2. Ooh, it's looking even more bell-shaped, right? It's looking a little even better. See this little bar here is coming down closer to the height of that bar. All right, we're going to go try one more here. We'll try 40 and see if it blows up, but I think that's about it. We're going to be able to go. Oh, still looking good. And what we notice is that as you start to increase that sample size, in other words, you start to increase the number of trials, the distribution gets more and more bell-shaped, okay? So we're going to go through that one more time in kind of high-speed motion here. Let's start off with a sample size of 10 and a p of 0.2. That looking kind of skewed to the right. Don't think I'd use that one, okay? I don't think I would use the normal approximation on that particular distribution. Okay, let's go 20 by 0.2, okay? Looking a little better, but that's still kind of skewed to the right. It's got some skew to it, okay? Remember, these are population models. These aren't data. If that was rough data, I would still go with a normal with it, but with a population model, you'd expect it to be a little more centered, a little less with the skew on it, okay? But come here about time I hit 30, it's looking pretty darn good, okay? It's looking like to me that that's symmetric enough that I could get away with saying that that's a normal distribution. All right, so let's go cut the chase here and let's find out exactly when it is we can use the normal approximation and when we can't. And it turns out that the conditions are as follows. It's based upon n and p, just like you saw with the graphs that we did. If n is big enough, then we'll have n times p will be greater than or equal to 5. But as we noticed when I had the p really large, not when it was just small, I had 0.2 of those examples I was just doing, when p was 0.95, I can get it skewed the other way. So we got to check both ends of it, n times p and n times q. They both have to be greater than or equal to 5. Now if that's a true statement, then you can use the normal approximation to approximate the binomial. That is, let me go ahead and I'll do it in the pen here, is what we can say is that we can say that the binomial of n by p is approximately equal to the normal distribution with mean np and standard deviation square root of npq. Now where to get the np and the square root of npq? Well, remember we talked about that just a minute ago. That's the mean from your binomial distribution, and that's the standard deviation from your binomial distribution. Okay, so how do we use this crazy thing? Well, let's go take a look at it, all right? So what if we had the same thing with wart removers again, right? And it states that it works on 95% of the warts. We have a total of 100 subjects are selected. What is the probability that 900 of the subjects, or more, I'm going to do the or more again here, okay? Switch this problem just slightly. I should have said or more to begin with, but we'll put it in right there. We'll have their warts removed. Okay, well notice that this time, again, we have a binomial distribution with an n of 1,000 this time, and a probability of success of 0.95, okay? Now, to tell you the truth, back in the day when I took this class, you got your binomial probabilities not from a calculator or a computer, but from a table of values, and those tables typically only went up to 15. And so pretty much a rule of thumb is that once you start getting 100 or more values of x in your binomial distribution, it's a good idea to check and see whether or not you can use the normal approximation to it. So the first step in seeing whether the normal approximation is going to work is to check what the values of n times p are and what the value of n times q is. You got to check both of those, okay? So n times p here is 1,000 times 0.95, which is going to be equal to what? That's going to be 950, isn't it, right? And then n times q is going to be what? Well, n times q, let's write that one out just so you see it. That's 1,000 times 0.05, right? Which is going to get you back 50. All right, so both n times p and n times q are both greater than or equal to 5, so the normal approximation here is good to go. We can roll with it, all right? So now, second step is to use the normal approximation. Well, how do we do that? Well, remember that we're going to approximate this distribution right here with a normal, so we need to state the normal we're going to use. Well, the normal we're going to use to approximate that binomial with is got mean of n times p and got standard deviation of the square root of npq, okay? So our particular normal distribution Oh, we already did n times p. It's right there. It's got a mean of 950. And let's go get that standard deviation here. Okay, so to get the standard deviation, we'll get out the calculator. Clear, clear. Okay, so what do we got? We've got second square root of n, which was 1,000. 1, 2, 3. Times p, which was 0.95, times q, which is 0.05. And we've got to close off our parentheses, okay? Which gets us back about, we'll go out 3 places, 6.892. Okay, so that's going to be the normal approximation that we're going to use. So let's get out a clean sheet here and let's go ahead and set this up, all right? So our distribution is normal with 950 is the expected value and a standard deviation of 6.8. Oh, make sure I get that number right again here. I don't want to get the wrong number there. 6.892. Okay. All right, so let's draw ourselves a glorious bell-shaped curve here, okay, for this distribution. It's not too bad. Okay, now x is going to be equal to what? Number of warts removed, right? That didn't change. The random variable is still the same. It just happens to be we're going to model it with the normal distribution now instead of a binomial one. We know that the mean here is at 950, okay? Now what did they ask us for? What is the probability that it works on 95% of the warts, okay? Or what, excuse me, 900 or more, that's what we wanted. What is the probability of seeing 900 or more removed, okay? So what's the probability of x being greater than or equal to 900, okay? Well, look, with the standard deviation of roughly about 7, notice that 900 is like way down here, isn't it, right? It's like even off my line, isn't it? So let's extend the line over here just a smidge so we've got someplace to mark it. So it's way down here, okay? So if that's where 900 is in my distribution, we can see that the shading here, oh my gosh, that's like what's the z-score? In fact, I'll let you do that. That's a great little thing. Stop the tape for a minute and figure out what the z-score is for 900, okay? Quick review. I'm not even going to give you the answer. You tell me what the z-score is going to be, okay? And so you find that that thing's way out there over to the left, isn't it, right? So the probability here is probably pretty close to 1, isn't it? So let's go ahead and do that calculation. So notice we're back to the normal. So we're back to our friend NCDF with the left endpoint equal to 900, the right endpoint equal to E99, the mean equal to 950, and the standard deviation equal to 6.892. Okay? So let's go ahead and do that calculation. So clear here. Second distribution, and we're going to use normal CDF. Okay, and let's see, what was our left endpoint again? It was 900. The right endpoint was E99. Our mean here was 950. And our standard deviation was 6.892. Close it off, and the calculator says, you know what, I can't tell any different from that and 100%. Now we know that's not exactly 100%, but as far as the calculator is concerned, that's the best answer it can give you. It's so close to 1, it can't give you any better of an answer than that. Okay, well that ends part 1 of this. Come back soon because I'm going to show you one more example of this, okay?